Hey there, Calc 3 folks, back here with what is turning out to be a rather long demonstration. We might call this part 3 here, where I've been showing you, to begin with, some different techniques for just graphing in Mathematica and how we produce, right, an illustration, right, as I've done here, for a region of integration, right? For this region over which we are integrating in a multiple integration process, where, I am just trying to give you some tools, right? What we've kind of developed here is a tool up above that will allow us to start to analyze these regions of integration, all right? What we might want to do is add to this tool, right, here at this point, where we start to take this a little further and continue into our understanding of this region of integration, right? And what we are actually calculating, that being this double integral calculation here, folks, where in this double integral calculation, we are calculating what's known as not a hyper yet, but a net volume calculation that's occurring between this surface here in three-dimensional space and this region R that we've defined in 2 dimensions. The region R, whose illustration we have put together here in our demonstration up to this point so far, right? What we might consider doing here is taking now this a little further, right, by mixing in that that double integral calculation with respect to function f. Right? And what we might start with is beginning to try to visualize function f. Right? In terms of visualizing function f here, we first of all have to put f into Mathematica, and Mathematica can handle single variable functions, as we've seen up here for g and x, for g and h. What we're going to do now is add in function f at x comma y, right? Which is done very similar to how we've seen it done with g and h, where we declare the name of our function followed by that operation, that wrapper around these multi-variables, right? Variable x and variable y, where the variables in our function notation are followed by the underscores, right? We are going to set this equal to, and you'll notice as I type that out there, it's going to say it needs to recognize x and y, right, as the variables. Here going to be x squared plus y squared in value, right? That's going to be our function. Now, I do want to show you something really quick here. If we were to maybe add a term on here and perhaps add the term x times y, you really have to be careful with multivariable functions that you clearly identify some of the operations occurring in your calculation. If I wanted to try to write on another term here for x times y, you will notice that it presents x times y. If I don't put a operator between x and y, right, it writes x and y in blue, which means that it's identifying it as a new variable, right? A lot like it's identifying f as a new variable, where it does not recognize that new variable as independent values back here in the function, right? The only variables it recognizes as independent is variable x by itself and variable y by itself. xy is being interpreted as its own value there, right? Its own variable interpretation. To separate that and think of that more as a product, we might want to put a product symbol between those two. Right? That will help to distinguish that as a product, or we could use a grouping symbol like a parentheses there, right? But just putting x and y by itself, side by side, inside of a description of a multivariable function involving variables x and y is going to cause some issues. So you do want to watch for that as you define your multivariable functions. All right, let's go ahead and remove that, though we don't need that in this case. And what we might consider doing here, after we look here at the plot of our region R, is we might start to try to understand, what the plot of f looks like, right? And the way we're going to do that is we are going to plot using a plot 3D function, right? Which we're going to wrap around function f at x comma y. right? And when we apply the plot 3D function, if I go over here and just look up how this operation is applied to a function, right? We can see plot 3D is going to be applied to function f, where to begin with, f is going to be evaluated across these bounds of x. Oh, sorry, I realize now you can't see. I keep doing this. I bring this window into view. Right here, we're our plot 3D is going to be happening here with respect to f, right? For these bounds on x, from the x minimum to the x maximum, and on these bounds on y, from our y minimum to our y maximum value. All right? What we've defined as our x minimum and x maximum value are these bounds that we might be using to help define this region of R. Right? We might say this is going to have to occur across bounds with respect to x and bounds with respect to y. Right? Where x might bound itself between, what have we used here in the past? For our plot here, we were using the bounds x minus 2 and x plus 2. We might go ahead and grab those again for down here. Right? And as for y's bounds, we were using these bounds that we used to help define the plot range, these bounds of C and D. Right? So y bounds, we might have those vary between C and D. Now that alone should be enough to get us the plot of that function's surface in 3 dimensions. And if we come down here, we can start to see that plot form here, right? Here is that surface. If we were to actually left-click on the plot, we can manipulate that surface in space by being able to rotate it around, right? And when I stop, it should return, right, to a little clear image, right? Not only that, we can also left-click on that image, hold down the control button, and be able to push it around in space in its current orientation. Right? If I let go, it should return to its original, well, pretty close to where we left it off. And then I believe if I hold the left click on the image, where I'm in that rotate mode, and if I hold down control, I can actually slide forward and backwards, zooming in and out on that 3-dimensional image. Right? That 3-dimensional image for my surface here. I might go ahead and reorientate that into space, right? Where, again, here, things are a little out of skew. Certainly notice. One of these axes is our x-axis, the other one is our y-axis, and then this vertical axis would be our z-axis. To actually see the axes labeled, we would use the axis label command. And again here, we're going to define those labels as a set, right? The set x, y, and z, right? It's going to have 3 labels. If I hit enter there, we should see those axes now come into label, right? Here's our x-axis, here's our y-axis, now here's our z-axis, right? If I want to kind of distribute the scale of this graph a little more, right? We can do that if we want to look at, for instance, the aspect ratios of this graph. That is using what we call the box ratios command, right? Or maybe I want to set up the box ratios here where we have a 1 by 1 by 1 ratio for each of the dimensions in space, right? And you can see there it kind of spreads out the x, y, and z axes, making them about the same in size for all 3 dimensions. It doesn't have that z-axis kind of squashed down there in space, right? And we are looking at this over our defined values of x and over our defined values of y. This is our surface. What we don't see is down here in the xy plane, we don't really see that region R, right? But region R would be existing down here in that plane, right? If I wanted to go about, right, if we wanted to go about adding here regions, well, this region R's description down here in this XY plane, we could do that by building up some more plots and overlaying them with another show command. All right. One of the first plots we would have to maybe build up if we wanted to, we might be able to define these functions g of x and h of x, defining the upper and lower bounds on R down here in this space. Right? And the way we would do that, if you remember in three-dimensional space, how we denote linear plots, linear graphs, is we have to use a parametric plot. So these are going to be defined using a parametric plot 3D, right? Where a lot like we saw back here for the parametric plots that happen in two-dimensional space, we are going to want to define a function of t, a function of x in terms of t, a function of y in terms of t, and now a function of z in terms of t, where t is going to have to vary across some t minimum and t maximum value, right? Where this function x of t, we might just define to be t, let x be t in this description. This function y at t, we might just let be g at t, right? The function g of x in this description, right? And then z at t, well, z in the xy plane, if we're going to be down here in this xy plane, that's where z is always going to equal 0. And this would be a parametric description of this curve g of x that's occurring here in this three-dimensional space that will happen in the xy plane. And that will happen for parameters of t that start at, now where should we start them? Perhaps we start them over the bounds that we have in the graph above, right? These bounds that were with respect to x from a minus 2 to b minus 2, where we'll just state those now in terms of t from a minus 2 to b plus 2 in value. Now, if we just look at that plot by itself, it should be the last plot we encounter here. We'll scroll down. There's our plot R. There's our surface. Here's that line in space. All right? If I want to combine and overlay these two plots, I may call this plot 5 in my picture, because I've already used plot 1, 2, 3, and 4. We might call this plot 6 in my picture. Right? And I'm going to overlay plot 6 onto plot 5 by showing plot 5 followed by plot 6. Right? And what that should do is show me my surface here. It's being overlaid on that image, right? We can see that parametric curve appearing down here in the xy plane. I could perform another parametric plot, right, for curve h of x, very similarly, just changing g of t to h of t, right, and then making sure that I overlay that also in my show command. But I'll often forget to put it into my show command, folks. And you will see that it's occurring down there now in the xy plane also. All right. In fact, we might be able to see it a little better if we make our surface a little bit more transparent. And you can do that by going in and adjusting the plot style of your surface and giving it an opacity measurement from 0 to 1. I believe 1 is 100% opacity. What we're going to look at is an opacity that's less than that. Maybe we go with a 50% opacity. Well, that would be maybe given by 0.5 in value. Right? And there we can actually see through the surface now. And actually we could dip that opacity down a little more. Maybe we dip that down to about 0.2, where we still kind of see our surface. Right? But underneath there we can also see that region R beginning to form down in there in the XY plane. And with respect to the mesh, right? If you want to have less mesh, I think that is mesh size, not mesh size, what is it? Mesh. Let's look up mesh real quick. Again, this is, we're just seeing some demos and a little bit of experience here. All none full. Mesh all, array mesh false. Let's go with mesh size. Well, I don't see it here. Oh, well, duh. It's just mesh. Sorry, it is just the command mesh. All right, I thought I'd have to set that. I could go none. Right? And it will make that with no mesh underneath the surface, which is kind of nice, but you lose some of the perspective of the surface, where you could adjust that down to maybe give a mesh of 8. All right? Where we should see, yeah, we see the mesh sort of spread a little bit further apart here. Or maybe we give it a mesh of 4. Right? We can certainly start to play with that. And I think that divides up our space. 1, 2, 3. Well, it uses 1, 2, 3, 4 meshes this direction. 1, 2, 3, 4 mesh lines this direction. Right? But again, that gives us a little bit more window space to kind of view our surface here. Right? And start to look at that region of R. Right? And again, learning some of these plot commands along the way here. What we might also add on then is these horizontal, well, what were the vertical lines back here in our two-dimensional picture. We could make those as parametric plots down here. We might call plot 8 equal to the parametric plot 3D. To make this vertical line at A, that would be when X is A, Y is T, and Z is 0. Again, right, being over values of T, where up here, what did we use? We used these bounds, right, on T. Notice we had to add this small little adjustment feature in order to have, when the case that these two bounds were at the same point, this parametric plot not bug out on us, right? Because it will do that, folks. So if I bring that down here as a bound, nope, somehow I missed the G of A. So we'll have that go from G of A to H of A with just a little bit more added on it, so that in case those do happen to fall at the, if the two curves happen to begin at the exact same value, we don't have the graph bug out on us. And then if we added that to P of 8 just to check that this is going to be accurate, right? There we can see that boundary coming into form. And if we just add another plot for the case at X equal to B, right? And consider that in our picture. Oh, not P8. Let's call that plot 9. Right, and overlay that into our image. Right. Oh, something's bugging here. Oh, I gotta adjust these bounds. This is also from G of B to H at B, not G of A and H of A. Make sure you adjust those bounds on that plot. So we should see that form nicely down there. All right? That is starting to define out that region R of space. We can see that's happening below our surface. Our integration is occurring across this surface over this region of R that's occurring down here in the XY plane. Right? If I actually want to highlight that region R as we have done above, then I'm going to use a region plot 3D, right? Where I will have, similar to the region plot up here, these bounds with respect to X and Y occurring in this region plot. But we're going to have to add one more condition for a bound. We have to keep in mind it's also going to expect, we're going to have a condition for z. And that condition for z in the xy plane, as we had seen in the parameterizations given above for our curves, we're interested in z being equal to 0. So how I add that command in here, or add that condition, that predicated condition here in this region plot, I would use a double equal sign, folks. When looking at conditions and using an equality condition, you do have to set that into Mathematica with some double equal signs. We are going to have this occur across values of x that we have given above. That would be from a minus 2 to b minus 2, and across these values of y. All right? Let me bring those down here. But we are also going to have to add in those dimensions with respect to z. Now z, right, in this case, we don't need much with respect to z. Let's just double check that. Let's go up here, region plot 3D. All right. It does look like it's going to want all three descriptions of x, y, and z. Now, we don't need to give much z in this case. We do definitely want to include starting at z equal to 0 and maybe going up to some value. It doesn't have to be a lot. We could probably get away with 0.1. Let's see if we can. All right. And there is our surface down there in the plane. And now what I did forget to do is, as I said, I often do, is I forgot to put this into my show statement. Well, I'll declare it as plot 10 in our picture here and interlay it into my show statement. And it should move this plot into here. And there it is, right? There it is down there in three-dimensional space, right down in the XY plane. You'll notice it will mesh it out as we see. We can ditch that mesh if we want. We can go back up in here and just turn the mesh to none. All right. And it will ditch the mesh across that region. So there we get that region highlighted there in just a nice orange color. And we could even change the color there if we wanted. Right, we could do plot style and maybe give it a light blue color, right, like we see in the graph in the picture given above. Did it do it? Or did we not get lucky? I guess that's light blue in Mathematica. I don't think we're going to... It may not adjusted. Plot style light blue. What if it was just to do... gray. Oh, that changed. I guess we're not going to get quite the hues that we're looking for, folks, though. But that would be our region R there. That would be occurring underneath this surface. Right? Between these curves, right? As we've defined. Right? This is kind of the picture we're setting up, right? In three-dimensional space. For, again, we go back to, right, this calculation right here. Right? This is the double integral across this surface. Here's our surface out in three-dimensional space. Right? Across, or over, we should say, this region R, right, that's defined down here in 2 dimensions, right, in the XY plane of 2-dimensional space. And what this is it's going to give us in its calculation is a net volume. The net volume of space trapped between this surface, right, the surface we have here, and this region R that exists down in 2 dimensions. Right? If I actually want to see that region, right, if I want to add that to my picture here, right, what I might do, right, we're going to call out another region plot in this situation. We'll call it plot 11. And what we're going to do is put those restrictions here on Z. Z, is now going to have to be bigger than or equal to the xy plane, which is at 0, and smaller than or equal to this surface being f at x comma y, right? And we certainly will have to have z expand out a little further than 0.1 there. What we notice is that z value back here in our plot, if we're actually looking at the plot here, let me get rid of this for a moment. Z goes quite large, right? Keep in mind, though, we can set it to some quite extreme values. It's only going to plot where conditions are true. So going up to 1,000 shouldn't really hurt things. And if we hit, oh, you know what I forgot is what I always forget. Let's do it this way. Let's put it into a whole new plot so that we get the region R's picture, because this is going to cover up region R. So we'll have both region R's picture and this solids picture. And here it comes. All right. There is our solid forming, folks. That is forming over that description of region R, you can see. All right. You'll notice it's a little choppy. Again, I go back to, it's because we're making a region plot, and region plots are going to work a certain way, as I explained back here, and what we may need to do is increase our recursion rate, right? We may have to come down here, and in this plot, increase our max recursions to a larger number. Let's see if 5 does it. And at the same time, let's add a little meshing. Let's add a meshing of 8 there and see what we get. So there's, right, region R by itself. There's the surface in region R over which we're integrating. And what we're calculating in the end is really the volume of this surface. Now you can see my recursion job there got a little better, but is not 100% great. I think the largest recursion we can actually set it on is 15, if I'm not mistaken. I don't think we can go beyond that recursion rate, at least not in the free program. I think in the paid version you can go higher, right? And yeah, we're still going to get some poor recursion there. Now, I'm not certain. Can we also use max points? Yeah, we might be able to get away with a max. No, it doesn't look like. Maybe we can do max points that way. Let's double check. This, if we increase our max points, let's see here, max plot points. Let's plot points. No. I thought we could increase that recursion there by increasing some points. Let me region plot 3D. Again, I'll explore over here. I'll jump into the details. All right. Permission, plot style, plot points. I think this is it. Plot points. That's what I may be missing here. Let's go with plot points. And maybe we go 15 there. Well, that may not be it. Because here it is. It is used in here. Plot points. It is used with that conversion there. Here they use 10 in their example. They got a good, but we can go higher. Let's maybe go higher then. We may be just shooting it too low. Let's go with 50. They do have 50 illustrated down below. See if we get a little nicer illustration there. Yeah, you can see it's starting to refine it, folks, right? Those are some ways to start using Mathematica to refine it. And because really what Mathematica is doing is it's guessing a whole bunch of XY values between these bounds. So maybe that's why we don't want to go too far out of bounds here. if we wanted to keep this between A and B, maybe that would increase our picture a little better if we went that way. Yeah, not so much. All right. Can we increase those max points, though, up to, will they go to 100? All right. Again, this is all playing around with Mathematica, folks, to get this. All right. Just start understanding ways of manipulating these plots. Notice it takes a heck of a lot longer, though, to render the plots. And you notice that did a pretty good job there, folks. There's still a little choppiness along that edge, but it's doing a pretty good job at rendering what would be that solid whose volume we are calculating in this triple integration here, or sorry, double integration of the surface over this region R. All right. Notice I keep throwing in there triple integration because this is all interrelated if you're that far in the lectures. Now notice, okay, so that does give us this region R, right? This is what we're integrating over. This is the calculation of the volume that we're calculating when we go back to what it is we are calculating, right? We are calculating this double integral, and as we've noted, this indicates a net volume. That net volume is what we see back here illustrated right in this picture. It's the net volume trapped between this surface F and this region R that existed down in the XY plane, where region R was defined as we have illustrated here, right? All given to us in these bounds on our integration, right, with respect to y and x. Now, to actually do this calculation, folks, with all this set up, to do this calculation is really quite simple, right? If we go over here to set up this calculation, right, what we are going to want to integrate, and this does happen in an iterative manner, right, is we are going to want to integrate function f at x comma y, first of all, with respect to, and I should take note, that's with respect to what? First with respect to y. All right? First with respect to y, where y is going to be integrated across those bounds from g of x to h of x in our iteration of integration. All right? You'll notice if I just enter in this moment, this will show me what the antiderivative would be evaluated across those bounds for my first iteration of the integration. Now, I did put it after this plot, so unfortunately it's going to take a while to render, but this would be that multivariate, well, that function in terms of x that would result. Now, Mathematica is going to kind of express it its own way if you wanted to. You could come along and apply a simplify operation to that, and it would express it in a simplified manner, right? Which may have been the way that it was originally presented. I'm going to turn off one of these plots, folks, because this is taking too long to render. Let's turn off. Now, how do you turn off a plot? Well, you just put some semicolons behind those show statements, and now when we go to render, it's going to render this. It's not going to render those other plots. And then it's going to render our statement there. So all that is this integral's result simplified. All right. You could even, instead of simplify, another way to look at it is to factor it. Right. It's a way to look at a result in a different way. Right. In a factored form. That might be convenient for you to learn. Right. There it is in its factored form. It doesn't factor too far. Right. At least not in what we might think of as a rational factored form. I do think it's presenting a rational factored form to you there, folks. But what we really want to do with this result is what? We want to, right, integrate it again. Integrate it now for a second iteration of integration across these bounds of x from 2 to 5. So the way we do that is we could, instead of factoring it again, just iterate that iterative integral again, right? Just take the integral of the integral. Where here we are going to now integrate the first integral's result with respect to variable x across those bounds from a to b. All right? And if we do that, we will see in the end the calculation here. Here is our calculation in its exact terms, right? If we wanted to give an approximation for that, right? As we saw, we could wrap that with what we call the numeric approximation operator, the n operator. And if I wrap that with the n operator, it will give me the approximation of that calculation out to several decimals. Let's see. Right? It gives us that volume, right? This is about 4,827.34 cubic units of net volume, right? Where if we wanted to get out to a few more decimal places, you can always then include in there how many decimals you're looking for. Maybe we're looking for this out to 8 decimals. Right? 8 digits of precision. And it goes out as, I think, as far as it as an exact value. This may be actually an exact value. Right? But it's going to do the best it can to approximating out to that length. And we do get a little longer approximation there. All right? We might highlight this as our integral. We might say here, this is the print command. We could have it print right before this statement. The net volume in this case is as follows. All right. So now when we calculate that, right, we get that statement beforehand, right? So we kind of can recognize that statement. And then if we want to put it all back into the big picture, right, we can drop out those semicolons, right, and perform the operation on this. All right, and what we get is our region R's illustration. We obtain the surface illustrated above region R. We obtain the actual solid whose volume we're calculating in that calculation, or the solid that illustrates that hypernet volume we're calculating. Right? And then we actually get the net volume. Well, we're not calculating a hypernet volume, the net volume, right? And then we actually get that net volume calculation. Right? Let's see here. Can I? Oh, going the wrong way. There we go. All right. Most of it above. The only thing I could see here to maybe address the program and make it a little cleaner is we put in constant bounds here. All right. We might want to declare these as variables. Maybe we call that M, and we refer to this as N, right? And maybe we adjust these up here, make these adjustable. Let's make M as our lower bound on Z. We'll start that at 0, and N will be our upper bound on Z, where here in our illustration, we may want to go up through 1,000. And you can see how just being able to start to build out these graphs is going to help you in setting some of those boundaries even. We could see this surface was going to go quite high over this region of space we're looking for, forming this solid. So we can use some of this information along the z-axis to help us set these bounds later on. Now this boundary for when z equals 0, we really don't need a tremendous bound there. We can just set it between some at least 0 and some other value. It really doesn't matter in that case. But here, because z is going to vary across these functions, we definitely want to have that across some variable bound. All right. See if this renders. Again, it takes a little while to render. That's because our max recursion and our plot points. All right. We could even set those to variable values. We might call that a max R, and we're going to call maybe these the P points, right, values. And we might even add those up here, right? Just make them adjustable. Let's see here. Yeah, that was max R values. What do we say? Those were 15, right? And then we have P points, plot points, and we got away with what here? We had 100 in that graph down below. Let's just make sure this program's still running. All right, R, surface, region R is going to take a while because of our recursion, because of our plot point settings, but it does render in a nice illustration, and we get our actual calculation down below. If we want to make it render a little quicker, we can always drop that value down. And maybe even that, let's leave plot points high, and we can play around with those settings just to see how long it takes these plots to start to render. Keep in mind we had a max recursion in there too. We could always make, that was this right here. Let's make that a max R2. All right, so that runs with a similar setting. All right. Can we get it to render here? Hopefully. And as it renders here, let me go ahead and wrap up with you folks. Again, this is my third demo. We're at about 40 minutes. I should start stopping this demonstration. But what you will notice is I have even given you the skills to start tackling your triple integrals, folks. Your triple integrals are going to be integrations across surfaces, right, in space that happen over region R's, right, and are going to be hypersurfaces, or that are going to occur, integrations that occur across hypersurfaces over solids, right? And you can see here I've given you the method now to even start to graph solids. The way we graph solids back here was these region plots in three-dimensional space. This is what gave me that solid description in 3 dimensions. This gave me the description. I kind of just cheated the solid description to come up with that region plot in 3 dimensions where z was set equal to 0. To graph my lines, I had to use parametric plots, and to graph the surface in 3 dimensions here, I had to use a 3-dimensional plot. Right? In order to do points are done by using, I think it's called a list point plot in 3 dimensions. That will plot points in 3-dimensional space. All right, if you wanted to plot a coordinate or two in 3 dimensions, that's the only plot I don't think I covered here in 3-dimensional space would be a list point plot. All right. But with that said, folks, I'll stop there. I may or may not have a demo for you coming soon. I'll just have to see with respect to time. But this should be enough to carry you through your study in multiple integrations if I don't get another demo out to you over some triple integration. I may, though, still try to put something together for you. We've gotten pretty far with our understanding here of the language with these first, couple hours of demos. And if you're this far and you've seen this and you watched it up to this point, you've seen quite a bit. So I'm not too worried about having given you this information down here on how to actually do our calculations here. But I do kind of want to warn you against making this a crutch. I am going to be looking for a lot of your work, folks, come test day and on your exams. But you can use this to certainly help begin strengthening your understanding and as a bit of a tool in your toolbox. All right. Maybe I'll try to share this code with you some way or another, this program. But if not, folks, you have it here. I've rolled through it with you. I think the best thing for me to do is probably leave it here and kind of force you to watch it. And if you're here, you've done that. So with that said, folks, I'll see you in the next video. Have a good day. Later. And I just realized I had this last window up in our last recording. So let me get rid of this window here, and I can roll through that one more time with you here, folks, as we wrap up. Let me fade that out, and we can see here. Here's the entire program. Right? Maybe I'll start at the top up here and just give you a slow scroll. All right, you can feel like if you need to pause it at any location, you can certainly do that. And maybe even I'll zoom in slightly, right, so we can see it maybe a little clearer on those fuzzier videos. All right, you can see I set some variables to be able to be set with our max recursion here, folks. And as I'm illustrating here, we have a program, folks. We've in a sense coded out a program here that does some math application for us. All right, and it's kind of nice. It's a cool tool to begin to learn how to use. So there it is, from top to bottom and bottom to top, folks. All right, so I'll clip this onto the last video, and we'll upload all this as soon as I get a chance. See you then.